Welcome to this video on the kinetic molecular theory, or KMT. And in recent videos, and if you've been doing a bunch of example problems, you've probably been dealing with the ideal gas law and other gas laws and plugging a bunch of numbers into equations to find values of pressure, temperature, and volume. But in this video, when we talk about the kinetic molecular theory, we're actually just going to state a number of qualitative principles, so really no numbers, that describe why gases behave in the way they do, why they follow things like the ideal gas law and the combined gas law. And these four tenets really, if we just summarize them in one sort of little picture, are just going to treat gases as sort of infinitely small little particles. I like to think of them as tiny grains of rice, just sort of being shaken around and moving around randomly. And so whenever you can't remember what a statement of the KMT states, just go back to this idea that particles are infinitely small. They don't really represent atoms or anything in the kinetic molecular theory. They're almost like grains of rice in a maraca, just being shaken about and not really interacting with one another or their environment. And so the first tenet of the kinetic molecular theory sort of follows from our little discussion of the grains of rice theory, if you will. And it states that gas particles are so small compared with the distances between them that their volume is considered to be zero. And so let's take a look at two examples of gas particles. First, we've got something like helium, or excuse me, what am I doing? Helium, He. Helium. And helium consists of, no, let's take a look at hydrogen. Let's take a look at hydrogen. That's what I wanted to draw. Hydrogen, H2. Hydrogen gas consists of two tiny little hydrogen atoms, like that. What about nitrogen gas, N2? Well, nitrogen is significantly bigger than hydrogen, and it's also diatomic. It's got two big fat nitrogen atoms. But the KMT says that the differing volumes of hydrogen gas and nitrogen gas are irrelevant. If we've got 1 mole of nitrogen gas, it's going to be almost exactly equal to 1 mole of hydrogen gas. And that's because the distances between the particles, things like this distances in centimeters, millimeters, and meters, are so much larger than the 10 to the minus 10 length of these, or volume of these, nitrogen molecules and hydrogen molecules, that we can consider their volume to be zero. And we can state this mathematically. I promised we wouldn't do any math, but I'm going to break that promise here. We can state this mathematically using the ideal gas law. And so we know that V is equal to nRT over P. That's just a statement of the ideal gas law. And so we see that volume, again, and we've talked about this extensively, is not dependent on a particle's identity. And so the volume of 1 mole of hydrogen gas is equal to the volume of 1 mole of nitrogen gas. Again, the identities and the differing volumes of the actual molecules are considered irrelevant. And that's the first tenet of the KMT. The second statement of the kinetic molecular theory says that particles are in constant motion and collisions with the walls of a gas's container cause pressure. And so if we just draw sort of a little container here, like this, with a few gas particles inside, then maybe we can zoom in on the wall. We've done this a bunch, and I think I've explained this in great detail, but there's no harm in repeating oneself. We know that these particles, if this is the wall of a container, and if it's rigid, we know that these particles inside, they're sort of swarming around, and every now and then they're going to bump into the side of the container. And we know that what sort of keeps a basketball inflated, what keeps the container of a gas inflated, is the pressure, or the force, exerted by these particles on the walls of their container. And so we know that if we increase the energy of these particles, we increase the temperature, which we'll look at in a later tenet of the KMT. We know that the pressure increases because more force is being exerted on the sides of the container. And so what causes pressure? Well, these little particles moving around and smacking into the outside of the balloon or the basketball, what have you, cause pressure. That's the second statement of the KMT. The third tenet says that gas particles are assumed not to attract or repel one another, and this is sort of counterintuitive. Let's say we've got two molecules of hydrogen gas. And so hydrogen gas consists of two protons. There's one. So each has two protons. And each has two electrons. Hydrogen gas is stable, it's unique in that it's stable with two electrons. And so say the two hydrogen gas molecules are arranged like this, and they're moving towards one another. We know that protons are positive, and so if these sort of the two ends of two positive protons are coming in close contact with one another, they're going to move like this. One is going to swerve off to this side, and one is going to swerve off to this side, because they repel one another. And similarly, if we sort of flipped this hydrogen gas molecule and had the negative electrons come into close contact with the positive protons of this hydrogen molecule, well, then the two hydrogen gas molecules would attract one another. They would exert a force on one another that pulls them closer together. The KMT says no. Yeah, sure, this happens on the extremely microscopic level, but remember, we're dealing with huge macroscopic systems. That's maybe a useful distinction to make. This is macroscopic. That just means sort of the big picture. We're dealing with liters, moles of gases, not the microscopic. We're not dealing with individual atoms, individual molecules. And so these particles are moving so fast, and there are so many of them, that these little contributions, these little attractions and repulsions, these are tiny, tiny forces, on the large scale are irrelevant. This is kind of a theme of the KMT. It says things that happen at the really tiny molecular level, like the difference in size between hydrogen gas and nitrogen gas, when we talk about the macroscopic picture, are irrelevant. So that's the third rule of the KMT, and now let's move on to the fourth and final rule. This is going to be quite a quick video, but you can always pause and rewind if it's confusing for you. Number 4, the average kinetic energy of a gas is directly proportional to its Kelvin temperature. And we're not going to prove anything about Kelvin. We'll just say that it's best to use Kelvin when you're dealing with chemistry, because Kelvin is the most accurate representation of temperature we have. But this should make sense. The average kinetic energy of a gas is directly proportional to temperature. And again, if we've looked at this example a bunch of different times in the last few videos. Actually, let me center this for you and zoom down a little bit. Say we've got some sphere of gas. We've got some sphere of gas with gas particles inside, and they're moving around happily. They're enjoying life. What happens if we take some logs of wood? That's a really poor log, but you get the idea. Take some logs of wood and light a crackling fire. Light a fierce fire. What's going to happen? Well, energy in the form of heat is going to be transferred to that gas, and we're going to increase temperature. So we're increasing temperature. And that's happening on the outside, that's happening on the macroscopic level. What's actually happening to the gas particles? Well, we know that if we heat something up, the gas particles move faster. They're going to move faster, they're going to interact with one another at a greater rate, they're going to smack into the walls of their container at a greater rate. And what does moving faster mean? Well, they're going to move faster. If we take a look at the fourth tenet of the KMT, we see that we're talking about kinetic energy. Kinetic energy, if you take in physics, you'll know it's just the energy is energy of motion. Energy of motion. So if we increase the speed of something, we increase its kinetic energy. So if we increase temperature, the particles move faster, we've also increased kinetic energy. And so that's how, when we increase temperature, we can increase the average kinetic energy of a gas, because on average, maybe a few particles are moving faster than others, maybe a few aren't moving quite as fast, but the average kinetic energy of a gas is going to increase. Perhaps you can also know this by just remembering that, well, temperature is defined as the average kinetic energy of a system. And so Obviously, if we have to increase temperature, by definition, the average kinetic energy of a gas is going to decrease. Similarly, if we took this sample of gas and put it in a freezer, the particles would slow down, they would move slower, and therefore the average kinetic energy of the gaseous system would decrease. And so we've just looked at the 4 principles of the KMT, and really you're not going to be tested on these too much. It's more just sort of a framework to help you understand things like the ideal gas law. But you may be asked a question like this. Use the kinetic molecular theory to explain a gas law. In this case, explain Charles's law. So pause this video, attempt to answer this law using complete sentences, and come back and we'll take a look at it together. Alrighty, welcome back. The first thing we've got to do in this question is just to identify what the heck Charles's law means. And if you've watched previous videos, you know that Charles's law just says that temperature is directly proportional to volume. And so if we increase the temperature of something, we're also going to increase its volume if pressure is held constant. How do we explain this using the KMT? Well, this is sort of like what we've said here. We know, let's just restate this statement, the average kinetic energy of a gas is directly proportional to its Kelvin temperature. So we know that if we increase the temperature of a gas, let's use white, if we increase the temperature of a gas, then by the KMT, then by kinetic molecular theory, the average kinetic energy of those particles will increase. Apologize, I'm a very slow writer. The average kinetic energy of those particles will increase. Okay, so now we need to find a way of relating temperature directly to volume. Well, let's take a look at another one of the tenets of the KMT. This says, number 2 says that particles are in constant motion and collisions with the walls of a gaseous container cause pressure. So they exert force on the container. So therefore, the gas particles will exert a greater force on their container. Now, 2 things can happen here. If we hold volume constant, a greater force is just going to increase the pressure of that system. But if we hold pressure constant, remember that's what we do in Charles's law, temperature directly proportional to volume, while pressure is held constant. If we want to maintain constant pressure and we've got a greater force acting on the walls of our container, well, we're going to have to increase the volume. And then so our final statement, let's just move down a little bit, we'll say that to hold pressure constant, volume must increase. Volume must increase. So what have we said here? We said if we increase the temperature of a gas, then by the kinetic molecular theory, the average kinetic energy of those particles will increase. Okay, they're going to be moving around faster. Therefore, the gas particles will exert a greater force on their container. Fair enough. That's the tenet number 2 of the KMT. And finally, we're going to link temperature and pressure, or excuse me, temperature and volume. We're going to say that to hold the pressure of the system constant, volume must increase. And so therefore, we've said increased temp yields increased volume, which is the exact same statement as we made up here to define Charles's law. So this is how you're going to use the KMT to solve problems. You're just going to qualitatively state what happens to a gas under certain conditions, and then try and relate those different conditions to one another to explain gas laws. So that's the kinetic molecular theory, and I look forward to seeing you in the next video.